Okay, so now we're going to look at some relationships between the moles, the mass, and the volume of gases. So first thing I want to make mention here is this, what you see on the screen. Remember we talked about STP conditions. It turns out that for any gas, 1 mole of any gas under these conditions, STP, its volume is going to be equal to 22.4 liters. And that can actually be shown based on the ideal gas equation, which we'll talk about later on. But for now, you can just accept this as true, that for any gas under STP conditions, where the standard temperature is 273 Kelvin and the pressure is 760 atmospheres, then the volume occupied by the gas will be equal to 22.4 liters. So 22.4 liters, this volume here, for 1 mole of a gas, that is known as the molar volume. So the molar volume is basically the volume occupied by 1 mole of any gas. And when I said any gas, I actually mean any gas. Any gas, whatever it is, if it's 1 mole under STP condition, the volume is equal to 22.4. So it doesn't matter if it's hydrogen sulfide or hydrogen or sulfur dioxide or methane, as long as it's 1 mole of the gas under STP condition, its volume is going to be equal to 22.4 liters. Now let me just point out that there's one error here for oxygen. Oxygen exists as O2, so its molar mass should be 32, not 16 grams. All right, so I just thought I should point that out. Okay, so for any gas, doesn't matter what the gas is, 1 mole will occupy a volume of 22.4 liters under STP conditions. So let's look at this question. This question gave you the density of a gas and is asking for the molar mass. Well, in this case, it's neon. Now, let me go to the pen mode here. So the question is asking for the molar mass. Now, we know that density of any gas, or any substance for that matter, is equal to the mass divided by the volume, right? What we could do is that we could say that the mass is the molar mass here, and the volume here can be the molar volume. The relationship will still be the same. The molar mass divided by the molar volume would be equal to the density of the gas. So the question is asking for the molar mass, and that would be equal to the density multiplied by the molar volume. So the density is 0.900 grams per liter, and the molar volume is 22.4 liters per mole. And this is because the gas is under STP conditions, as the question says up here. So therefore, the units that will cancel out would be the liters, so your answer would be in grams per mole. So let me do my thing on the calculator. 0.900 times 22.4, and according to my calculation, this works out to be equal to 20.2. So 20.2 grams per mole. All right. Okay, so that's that. All right, now let's talk about densities of gas. We all know what density is. Density is, by definition, mass over volume, which is what we stated in the example we just did. So when it comes to gases, we typically express the mass in grams when we're calculating the density, but the volume is typically expressed in liters. All right, so what you'll find is that the units of density for gases is normally expressed in terms of grams per liter. All right, now the thing about gases is that because they are so responsive to changes in temperature and pressure, what you'll find is that the density of gases will be affected. All right, because of course, if you change the volume here, let's say you increase the volume, then because you have m divided by v, if the volume increases, the density will decrease, and vice versa. All right, so we can use that idea to solve this problem. Question says the molar mass of sulfur dioxide is 64.07. Determine the density. Well, the density in this case would be equal to the molar mass divided by the molar volume. The molar mass is given as 64.07 grams per mole. The molar volume, because it's under STP condition, will be 22.4 liters per mole. And when we do the calculation, 64.07 divided by 22.4, I got 2.86 grams per liter. So this becomes 2.86 grams per liter because the mole units will cancel out. Okay, let's talk about the ideal gas law. Now, the ideal gas law is the equation that ties in everything: the pressure, the temperature, the volume, and the number of moles of the gas. And this is the ideal gas law right here. PV is equal to nRT. Oops. So the P here is the pressure, which must be expressed in atmospheres. The V is the volume, which must be expressed in liters. The N represents the moles, and the T is the temperature, which must be expressed in Kelvin. And the R that is shown here is called the ideal gas constant. So it's a constant of proportionality, and it does not change. So everything else are variables, but the R value is a constant. And if the pressure is in atmosphere, is the volume is in liters, and the temperature in Kelvin, then the units of R is shown here. It is, let me go back to the pointer mode. It is liters atmospheres divided by mole Kelvin, and this is the value 0.0821, all right, for R. So basically we can use this equation if we know any one of these items, and or if you want to find out any one of these terms and you are given the others. All right, all you have to do is rearrange the equation to get what the question is asking for. So here's an example of this. Let me go back to the pen mode. So in this example, they gave you the moles of helium gas, they gave you the pressure, and they gave you the temperature, and they're asking for the volume. So the equation you're going to use is PV is equal to NR. Okay, what's going on with this? RT, and the aim is to find the volume. So if I rearrange this, I'm going to get volume is equal to nRT over P. And all we have to do is plug the numbers in. So for the volume, the number of moles is equal to 5.00 moles times R, which we said is 0.0821 liters atmospheres over mole Kelvin, times the temperature. Now the temperature is 25 degrees, so we have to convert that to Kelvin. So when we add 273 to 25, you're going to get 298 Kelvin. And then we divide all of that by the pressure. Now the pressure has to be expressed in atmospheres. They gave us the pressure in torr. So what I would do here is that I would multiply this by 1 atmosphere over 760 torr. And that's it. That's a setup. In terms of the units canceling out, the torr units will cancel out here and here. Atmospheres cancel there and there. Kelvin cancels here and here. Moles cancel there and there. So the only unit remaining would be liters, which comes as no surprise because the question is asking for the volume. So let me do this. 5 times 0.0821 times 298 divided by parentheses 750 divided by 760 close parentheses equal, and the answer I get, let me do this again, I think I made a mistake. Okay, the answer I got is 124 liters. So let me put, whoops, come on, 124 liters. I could be wrong, but that's the answer I got. All right, so that's how we do that. All right, now we can actually use the ideal gas equation to get another equation which allows us to determine the molar mass of a gas. So if we start off with using uppercase M to represent molar mass and lowercase m to represent mass in grams, then we know that the relationship between the two is given by this equation. Uppercase M, the molar mass, is equal to the mass in grams divided by the number of moles. So if we rearrange it, we can get the number of moles is equal to the mass in grams divided by the molar mass. Now, as far as the ideal gas equation is concerned, we can also rearrange it to get an expression for N. In that case, N will be equal to PV over RT. So therefore, we can basically equate these two equations because they're both equal to N. So when we do that, we're going to get this relationship. Lowercase m divided by uppercase m is equal to PV over RT. And then when we rearrange it to solve for lowercase m, which is the molar mass, we're going to get this equation. So we can use this equation to calculate the molar mass of a gas if we have all these terms. All right. So that's one useful equation when it comes to determining the molar mass. And this comes, as I said before, from the ideal gas equation. All right. So we can use that equation to solve a problem of this type. In this question, they're asking for the molar mass of a gas. They gave you the mass in grams. They gave you the volume in milliliters. They gave you the temperature in Kelvin and the pressure in atmosphere. So remember now, the equation is uppercase M is equal to lowercase m RT over PV, right? So all we have to do is put the numbers in. For the mass, that's 0.020 grams times R, which is, of course, the constant, which is 0.0821 liters atmospheres over mole Kelvin, times the temperature, which is 305 Kelvin, all divided by the pressure, which is equal to 0.054 atmospheres, multiplied by the volume, which is 250 mils, but we have to convert that to liters, so we have to multiply by 1 liter here and 1,000 mils down here, and that's it. Work that out, and that would be the molar mass. So let's do that. 0.02 times 0.0821 times 305 divided by 0.045 divided by 0.25, and the answer I got is 44, or call it 45, and the units in this case would be, well, let's see here, the atmospheres cancels here and here, milliliters cancel, liters cancel, Kelvin cancel, so basically the only unit remaining is grams divided by moles, so it would be grams per mole. And that's how you do that. All right. Okay, moving along. Well, actually, we'll stop here. The next video is where we're going to start talking about combining what we learned in this chapter concerning gases and what we learned earlier in terms of stoichiometry. So until next time.